good morning. We will continue with rocket nozzle today. If we recall what we did in the last class, we told ourselves if I have a chamber, let us say any chamber, and this has a gas at a pressure Pc, temperature Tc, the molecular mass of this gas is m gram per mole, and I sort of expand this gas out through a small opening which we called as a vent. We were able to calculate the exhaust jet velocity in meters per second. We found out the condition for which Vj is quite large. We told ourselves, well, the temperature must be large, the value of the chamber pressure must be large, and the molecular mass must be small. We also examined the variation with respect to gamma, told ourselves gamma is not very influential, especially when Pc is small, or the ratio, if I say the exit pressure is Pe over here, when the value of Pe by Pc is somewhat high or the Pc value is small compared to Pe, then gamma is not influential. This is what we showed last time through the expressions which we derived. Now, whenever we have a rocket, we told ourselves, well, impulse is equal to mass which is ejected into the jet velocity, or rather we say that the force is equal to d by dt of I, which is equal to m dot into Vj. Therefore, we are interested in a high value of this velocity with which the mass efflux leaves the chamber. Therefore, the question is there anything like a configuration or shape of vent which can give me a high value of jet velocity, and this is what I get started with. Then we will go back and try to find out what are the conditions for this high jet velocity. We will have to look at matching of the exit pressure with respect to the chamber pressure, and that is what I propose to do in today's class. We will also physically try to understand, is there anything like some information transfer between the outside and inside of a chamber. Let's get started with this background. Let us first say, well, I have a nozzle, and this nozzle I am interested in the shape, therefore I say, well, let me have a shape like this. The shape is such that at a distance, let us say this is x is equal to 0, at a distance x from the initial origin, that means this is x over here, let us say the area of the vent is A, let the density of flow through this be rho, let the velocity of flow be v at this particular section x at a distance 0 from this reference plane which is over here. Let us consider the variation in the properties at a distance x plus dx. The area is different from A because I want to find out the configuration of this particular vent which gives me the maximum Vj. Therefore, to be able to derive that, I say let the area at dx be A plus dA, let the density at this section be rho plus d rho, and the velocity at this section be v plus dv. My main aim is to find out what must be the shape such that I get a high value of Vj. Therefore, I just look at these two sections, let us say section 1 at which the area is A, density is rho, velocity is v, at section 2 dx away from this at which the area is A plus dA, a small change in area. I think according to this figure dA should be negative, but I just have a general thing A plus dA, let the density be rho plus d rho, the velocity is v plus dv. Therefore, now I say that the flow is constant. In other words, whatever comes here is this, I consider a steady flow through this particular opening or vent, and when I consider a steady flow, I have the mass flow rate m dot in kg per second is equal to rho a v through the section 1, and the same thing flows through the section 2 which is equal to rho plus d rho that is the density at the section 2, into A plus dA into V plus dV, right, and this is the mass balance equation. Since the flow is steady, the same mass flow rate flows through this section and this section. Let us solve this equation, and what do we get? Mass flow is a constant, or rather dm dot must be 0 because mass flow is constant. Therefore, I get the expression d of rho AV is equal to 0, and therefore, now if I were to expand it out, I get rho A dV plus I have AV d rho plus rho V dA is equal to 0, or rather I divide this entire equation by rho AV and I get dV by V plus d rho by rho plus I get dA by A is equal to 0, and this becomes my mass balance equation in the differential form. I could have derived this expression by just saying rho AV is a constant, therefore logarithm of rho AV is a constant, and differentiating this would have given me dV by V plus d rho by rho plus dA by A is equal to 0, which we call as the continuity or the mass balance equation. Now, why did I derive this? I wanted to find out what is the change in area which will give me a high value of velocity, and therefore, my aim is to relate dV by V with dA by A. Unfortunately, I am left with d rho by rho, and I get d rho by rho because the flow I assume is compressible, the density is changing, and therefore, I am left with one term here d rho by rho, which I should express either in terms of dV by V or dA by A to be able to find the dependence of velocity on the change in area. Therefore, to do that, I again go back and ask myself, can I write one more equation? Let us say the momentum equation. What does the momentum equation tell me? The momentum equation tells me the rate of change of momentum must be equal to the impressed pressure or impressed force. Therefore, let us write the momentum equation. The mass flow rate is m dot, the change in velocity is v, rate of change of momentum is the change of velocity is from v to v plus dv, that means dv minus v, that means m into v plus dv minus v is the rate of change of momentum, and this is balanced by the force. And what is the force what I get? I have the change in pressure across is dP and the area is A. I find dP is higher, therefore, the force acts in the direction of change of momentum, and therefore, I have mass into change of momentum is equal to the force. And what is the m? M is equal to rho AV into V and V get cancelled, dV is equal to minus A of dP, A and A get cancelled, and therefore, I get rho V dV is equal to or plus dP is equal to 0, which becomes my momentum equation or pressure balance equation. See, we must be able to generally derive the momentum equation by just applying the Newton's second law, saying, well, I have a mass here which flows across here, the change in velocity is dV, the rate of change of momentum is m dot into dV, and that you have the pressure force which acts on the mean area into dP is the change in is the force, and therefore, this is the force balance equation. Therefore, now I find, see, I wanted to get rid of d rho, but now I have got an expression in terms of dP. Now, how do I still get rid of this term in some way, and to be able to do that, we have to look at little bit on sound velocity. What is the sound velocity? It is very central to gas dynamics. The notion of sound is central to gas dynamics for the following reason. Like, for instance, I talk to you. When I talk to you, the sound waves travel, we say, at the speed of sound, and we say that the speed of sound, let me erase this out. I have a sound wave which is travelling at a speed of a. And what do you say when the sound wave, you hear the sound wave, you get a little bit of pressure perturbation by which maybe your ear responds, or you get some velocity perturbation, maybe I get some velocity perturbation, I get some pressure perturbation, maybe I could even get a very small temperature perturbation. If the sound intensity is large, maybe the temperature could be high. Therefore, let us take a look at what this sound wave means and how do I introduce sound wave into that equation. And towards the end of this course, we will try to see the importance of sound wave when I talk of the flow. Let us get started. Let us imagine I have a pipe here and I say a sound wave propagates in this pipe. I take the same medium, I take some medium of a gas. Let the pressure of this medium be P, let the density of this medium be rho and the temperature of this medium be T. The medium, let it be stagnant like the room temperature room over here, that means the velocity here is equal to 0. In other words, I am just looking at the sound wave propagating in a stationary medium, that means velocity is 0, of pressure P, density rho and temperature T. And what happens when the sound wave propagates through the medium? Let us say the sound wave, it has come here, it increases the pressure little bit by P plus dP. Initially velocity is 0, I could have a velocity dV, it perturbs it, I have a density rho plus d rho and temperature could also change. Now I want to write an equation for this particular medium. Now what is happening? I am standing over here, this is my frame of reference, I am watching the sound wave go by, the sound wave processes this medium which is initially stationary, increases the pressure by dP, increases the velocity from 0 to dV of the particles, maybe the density changes from rho plus d rho, and that is what I am watching. And for me to write the equation standing here to see the wave and what is the velocity of sound, I say that the sound velocity is a meters per second. I just presume it is travelling at a constant speed of a meters per second. Now it is very difficult for me because this is moving to write the equations of motion, and therefore I transform this into the frame of reference. Instead of me standing here and watching the wave go by, I position myself on the wave, and now I can find out what is the difference over here because nothing is happening. And if I stand on the wave and I am moving along with the wave, I see the gas coming towards me with a speed a meters per second because I have told that the wave moves with a velocity a. And now the conditions here are P rho, perhaps T over here, velocity is a now, and I had, when the velocity was 0, I had dV, therefore the velocity here is a plus dV, the pressure is still the same P plus dP, the density is rho plus d rho. I think these transformations are important in the sense, I initially watched the sound wave go by, I am talking, I see the sound wave going, but if I stand on the wave, what is it I see? Since I am moving, I put myself on the wave, therefore the thing is coming over here and I have the changes happening over here. Now I write the equations for this. What will be my equations which I will get? I have over here on the right hand side undisturbed medium, this is the disturbed medium, I stand over here, watch the fun, I am writing the equation, I get rho a is the rho a into cross sectional area, I take the same because it really does not matter, and rho a is equal to rho a into a, and a here cancels, rho plus d rho into a plus dV. This becomes my mass balance or continuity equation. You see the similarity of this equation to this particular equation wherein you have rho a v, here we considered a variable area. I just wanted to find out how the sound wave travels and therefore I write this. Let us simplify it. I have rho a is equal to rho a plus d rho into a plus rho into dV plus I have d rho into dV. But mind you, we are talking of sound wave is travelling at a speed a meters per second. We also know that the pressure perturbations dV is small, the density perturbations d rho is small, therefore I can for all practical purposes say this is equal to 0. And therefore what is it I get from this equation? I get rho a get cancelled, I get the value of rho dV is equal to minus a d rho. This is from the continuity or mass balance equation across a sound wave as I sit on this sound wave and I see the medium processing. Okay. I now write the momentum equation. What should be the momentum equation? Well, I am standing here, I see the change of momentum, that means I see rho a is the mass flux which is coming over here, and what is happening? I have the velocity changing from a to a plus dV, rho a dV is the value of the rate of change of momentum, and that is balanced by the change in pressure is equal to 0, which by observations I write. I do not need to again go back and derive it. This is the rate of change of momentum, this is the pressure, change of momentum per unit area, therefore force per unit area is 0, and this becomes my momentum equation. Now I look at this equation which I call as equation 3, because I have already derived the continuity equation which was 1, and I have the mass balance or momentum equation, let us call it as equation 2. Now I look at the momentum equation I call as 3 over here. Three is the mass balance equation, 4 is the momentum equation, and therefore if I were to solve these two equations together, I have rho dV from this equation. Let us put it together. Rho dV is equal to minus dP by A Therefore, if I were to substitute rho dV over here, what is it I get? Minus dP by A is equal to minus A d rho, and what does it give me? It gives me that dP by d rho is equal to A squared. That means the velocity of sound square is equal to the ratio between the pressure perturbation to the density perturbation in the wave. But that is when I am talking to you all, the type of perturbations which I get in pressure and sound and density behind the wave, the ratio of that is equal to the sound velocity square. Now I get this, maybe I call it as equation 5. Let us come back and deal with this a little later, because we should not lose focus of the problem, because I wanted to get rid of d rho by rho, and therefore if I were to now write d rho is equal to dP by A square, I am going to get from this equation I get dV by V is equal to plus d rho by rho, d rho I take here, therefore I get dP by A square and d rho is equal to dP by A square. I have 1 over rho plus dA by A is equal to 0. Now I go back and say, well, I know dP is equal to rho V dV, and therefore if I were to substitute the value of dP as minus rho V dV, what is it I get? I get the value as dV by V plus, now I get minus because I have minus rho V dV, and rho gets cancelled, therefore I get V, and on top that is dP is equal to V dV by V dV, rho gets cancelled, V by A square into I get the value of dV plus the last term, that is equal to dA by A is equal to 0. What does it have done? We substituted the value of d rho by rho and go in terms of dP by A square into 1 over rho, because we found that dP by d rho is equal to a square, and therefore this became the substitution, and then we wanted to write get rid of dP in this, and therefore we use the momentum equation which we wrote as minus rho dV. Therefore rho dV, that means minus rho dV, that means minus V, rho and rho get cancelled, dV by a square, that means minus V dV by is what we get over here. Please check if it is all right. Let us simplify it and write it down over here. Therefore I get dV by V into 1 plus. Now I get an expression, I took V outside at the denominator, therefore I get V square on top divided by a square, because I still have a square, plus dA by A is equal to 0, or rather now I just blindly say let me call Mach number m as equal to the velocity of the medium divided by the sound velocity. I will come back to the physical significance of this a little later, and therefore I can write dV by V is equal to minus dA by A into 1 over, I get, yes I have minus here, let us go back and look at this. We had 1, we had minus there, therefore we had 1 minus V squared over here, because what happened was we had substituted dP and that dP was minus there, therefore we had minus V dV. Please be careful about these signs. Therefore this is the expression what we get. Now let us, whenever we derive an expression we must look at the what is happening behind it. Therefore what do we find? If dA is negative like what we had drawn here, what did we draw? We said area is decreasing as x is progressing. If dA is negative, this becomes positive, and if we say m is less than 1, when dA is negative, then dm is or dV is positive. What is it I am telling you? I want the velocity to increase as the flow progresses. If for velocity to progress, if m is less than 1, I get this to be a positive number, it is still minus of this, therefore unless I have area which is decreasing as x proceeds, I cannot have a positive value. In other words, I tell myself flow will accelerate or flow will increase in velocity if Mach number is less than 1, dV will be positive if we have dA to be negative. In other words, all what we are saying is the cross sectional area, if I have a subsonic or a Mach number less than 1, then I should have something like this for velocity here at section 2 to be greater than at section 1. That means here it enters at lower velocity, dV gets increased, I have a high velocity over here. That means for the case of a subsonic flow or a flow for which Mach number is less than 1, flow will accelerate in a converging passage. On the contrary, using the same set of arguments, if I have a case wherein the flow takes place in a diverging configuration, then if I have Mach number greater than 1, then what happens? Mach number is greater than 1, this becomes negative, negative and negative gets cancelled, therefore dV by V goes as positive of dA by A. In other words, the flow accelerates if Mach number is greater than 1, dV is positive if dA is positive, right. See, through the simple argument of looking at the mass balance and the momentum equation, we are able to come to the conjecture that maybe in a convergent section velocity will increase only if Mach number is less than 1, whereas if I have a divergent section and if Mach number is greater than 1, then only the flow velocity will increase. What will happen if the Mach number is 1? If Mach number is 1, the equation sort of breaks down. In fact, I find Mach number is 1, then I have 1 over 0, and unless I have dA by A equal to 0, this equation cannot predict anything at all. Therefore, I tell myself if Mach number is 1, maybe I must have a constant area, that means A is constant, or rather dA must be equal to 0 for a flow to take place. Therefore, all what we have done so far is we looked at the continuity and momentum equations and found that in a vent or in a small opening we should have initially the flow should come like this, it should come to a value of m is equal to 1, and then it should pass through the divergent such that dV is positive here, I have dV is positive, and therefore I can have acceleration of flow, and therefore along this particular length if I plot the velocity, maybe the velocity will keep increasing, and at over here the velocity must be equal to the sound velocity. Therefore, in order to get a high value of jet velocity, what we require is we must have a minimum area, and this minimum area like my throat, which is a minimum area, I call it as throat. Therefore, we start with a large area, we converge it, we increase the velocity to a value, velocity is equal to the sound speed at this section, which is equal to Mach 1, and thereafter the Mach number is greater than 1 and the flow velocity increases, and therefore I can have a high value of jet velocity. Therefore, the configuration of the vent should be a convergent followed by a constant section which I call as a throat, followed by divergent if I have to get a high value of Vj. Supposing by chance when I am doing all this, my mass flow rate, like I considered a balloon which had a pressure of Pc, I had Tc, I had molecular mass and rho c over here, if it is such that the mass flow rate through this is less than Mach equal to 1, then what is going to happen? Let us say I have the same configuration, in other words I have the convergent followed by the throat followed by the divergent, and if by chance my velocity is less than A here, that means Mach number is less than 1 at the throat section, then what is going to happen? Well, I now plot velocity as a function of distance. The velocity keeps increasing up to this place, but I find that V is still less than the sound speed here, or rather the Mach number here is less than 1, and therefore the Mach number here is less than 1, and therefore the velocity drops further. That means in the convergent the velocity increases, in the divergent velocity decreases, and this portion divergent is what we call as diffuser. A contraption which decreases the velocity and enhances the pressure is what we call as a diffuser, and a contraption which increases the velocity is what we call as a convergent or the nozzle section, and this total is what we call as a nozzle. And therefore, if I can have Mach number 1 at the throat and then I have a convergent followed by divergent, I can get a high value of jet velocity. That means Mach number at the exit will be a large value. See, therefore, from the simple writing or simple expression of continuity and momentum, we tell ourselves, well, if I have a rocket chamber, it is necessary for me to have a chamber, and I should have a convergent section followed by a throat section followed by a divergent section, and this is what gives me a high velocity, and this is what I call as a nozzle, which I find is a convergent divergent nozzle, which in some textbooks is also written as de Laval nozzle. But let us be very clear, if by chance I do not get m is equal to 1 at the throat, well, the buildup of velocity in the convergent is lost in the divergent and the velocity drops. And this is the configuration of a nozzle, and we find that all nozzles, in order to give me a high jet velocity, should be a convergent divergent nozzle. Let us go through the exercise, because this is central to having a high jet velocity. Let us find out the variations of parameters across a convergent divergent nozzle. Let me first sketch a nozzle here, convergent, maybe a throat, maybe a divergent, and let us assume that at the I have such a flow rate that I have Mach number is equal to 1 at the throat. Now let us find out what is the change in dV by V along the length. We just now found that dV by V increases up to the throat, and then it further increases over here. Therefore, dV by V, because Mach number is 1, the characteristic of the equation changes, m squared minus 1 becomes negative, and therefore dV by V is like this. If dV by V is like this, well, V by the value of velocity would also keep changing, and what I get is maybe the velocity increases like this. If the velocity increases, what is going to happen to the pressure or the density? Let us plot a few more parameters. Now instead of dV by V, I am going to plot, let us say, the variation of pressure, that is, let us say, dP by P. How should it look like? How should the variation, or I know the velocity, I want to find out what the pressure variations, or let us find out the first one, the let us say the variation of d rho by rho, because we already had an expression which we derived. Let us write that expression again. We had the expression dV by V plus d rho by rho plus dA by A is equal to 0, or rather we have d rho by rho is equal to minus of dV by V plus dA by A. I know the value of dV by V increases like this, therefore d rho by rho will be negative and dA by A initially is negative. In other words, if I were to say this is my throat region, that means I have Mach is equal to 1 here, this is my length x along the nozzle which I am considering. I find therefore the density will keep falling. And what happens at the throat region? At the throat region I had 1 minus m square at the in the term over here, therefore I have something like a steep gradient in velocity. I have a very steep region here, and d rho by rho comes over here. I think this is important. In other words, the density keeps decreasing. At m is equal to 1, there is a rapid change in d rho further, and further d rho by rho changes, and this region at the throat is a region of rapid density change. In fact, we will find, and when we get into this problem of combustion instability, we will find that when we have a rocket nozzle, let us say I have a rocket, I have a convergent divergent section like this, the rapid decrease in density or rapid change in density over here acts as if it is a solid. There is a very rapid change, therefore it tends to be as a closed end and not as an open end. We will come back to this, and this is important. That means at the throat portion you have somewhat a large change in this, and therefore if I were to now plot my density as a function of x here, I have the throat over here, well, the density keeps decreasing. Therefore, for a convergent divergent nozzle for which m is equal to 1 at the throat, velocity change increases, velocity increases, density change decreases, and the density decreases. Now there are two other parameters which are left. What is going to happen to the temperature, what is going to happen to the pressure? You know, anyway we made an assumption when we talked in terms of the vent. We told ourselves the flow through the vent is adiabatic and is reversible, therefore P by rho to the power gamma is a constant. I know density changes, and therefore the pressure, if I have the throat at m is equal to 1, well, the pressure should also decrease. This will be my variation of pressure with respect to x. and we also had derived an expression which said the temperature 1 divided by temperature 2 is equal to P1 by P2 divided by, we had gamma by gamma minus 1, or rather yes, P1 by P2 was T1 by T2 raised to power gamma minus 1 by gamma, and therefore the temperature, if I have the throat here, should also decrease, and this will be my temperature variations with respect to the distance x. See, all what we are telling is the pressure decreases in a nozzle monotonically, the density decreases in a nozzle with rapid change in density happening at the throat, well, the velocity increases. This is all what we have said, and this is something which all of us know. Now let us put some other parameters. If I want to plot the sound velocity variations, what will it look like? In other words, I have the expression A, I want to plot how the sound velocity will vary along the length, and I tell myself at the throat the Mach number is 1. We again go through the expression what we derived today. We told ourselves dP by d rho is equal to a square. Now we told that the nozzle flow is isentropic, that is adiabatic and reversible, therefore we have P by rho to the power gamma is a constant. Therefore what is a square? Let's write that out. P is equal to a constant rho to the power gamma, therefore dP by d rho is equal to gamma c into rho to the power gamma minus 1, and therefore now if I were to write the value of c as equal to gamma p rho to the power gamma into rho to the power gamma minus 1, or this is equal to gamma p by rho. Therefore we find that the sound speed is equal to gamma p by rho, and for a perfect gas or for an ideal gas, P is equal to rho RT, or this is equal to gamma RT, or sound speed is equal to under root gamma RT. Therefore what is it I find for sound speed variations? I will find, well, the sound speed starts at a high value of sound speed and it keeps on coming and it comes like this. One last parameter I can still think of is the Mach number at variations along the, I know the velocity variation which I had over here, velocity changes along the x over here in this particular form. I also find that the sound speed keeps coming down, and therefore if I were to find out the Mach number variations as a function of x, what is it I get? This is numerator is increasing, denominator is decreasing because Mach number is equal to v by a, and therefore maybe if this is my plane, well, it is going to come like this and going to go like this. I think this is fundamental to any nozzle flow, any expansion, and we must remember this. Therefore let me repeat it again. dV by v progressively increases when I have Mach number 1 at the throat, velocity increases, the density decreases rapidly at the throat, pressure also decreases, temperature decreases, the sound speed decreases along the length, and therefore the Mach number increases along this. And we are interested in a high value of Mach number or jet velocity at the exit. If now I were to tell myself, if by chance the Mach number at the throat is not 1, that means I have insufficient pressure over here to give a high jet velocity equal to the sound speed. In other words, I now get, let us say, Mach number is less than 1. What is going to happen? dV by v is going to increase over here, it is still less than the sound speed, that is v is less than a, and therefore it falls down here. That means my value is like this and comes down over here. Velocity increases up to the throat, but it is still the sound speed is less than the velocity is less than the sound speed, and therefore it comes over here. What happens to the density? Density falls up to the throat and increases back. Therefore, I have a diffuser section here. Density again same picture, and now we say Mach number is less than 1. Now I say Mach number is less than 1, the pressure recovers here, instead of falling it recovers over here, temperature recovers over here if the Mach number at the throat is less than 1, and similarly the sound speed falls up to the throat and recovers over here, that means it now becomes less than 1, and therefore I have the same portion here, the Mach number going up to this and coming over here if the value of Mach number at the throat is less than 1. I would request you all to go back and study these figures again, because this is central. You know what we find is, well, I must have a convergent section followed by a divergent section, and in between I must have a constant area section which I call as a throat. Is this clear? I think this is central. Therefore, we now tell ourselves, if I want to have a high value of jet velocity, it is essential for me to now have a convergent followed by a throat section followed by a divergent section with the condition that Mach number must be 1 or velocity must be equal to the sound speed at the throat. And then if I have this, velocity keeps increasing and I can get a high jet velocity at the exit, and this is what is the central theory of a nozzle, which we call as a convergent divergent nozzle. If I find that I have inadequate pressure, that like for instance I have a cold gas, I have inadequate pressure and I cannot have Mach number greater than sound speed or Mach number equal to 1 at the throat or velocity is equal to sound speed, then it is better my nozzle is like this, such that my jet velocity is still less than the sound speed. That means if I have inadequate pressure or inadequate conditions here such that I cannot get here, then I must do away with the convergent section, because if I have this divergent section over here, I am really losing thing, I am not really gaining thing. Therefore, whenever a rocket nozzle has to be designed, we have to ensure I have sound speed at the, that is the velocity of the flow at the throat must be equal to the sound speed. Okay. Now I will ask myself one last question, what is the significance of sound speed? Is there something very significant about it? Did I do something, I just introduced the sound speed through the equation, and I told myself that in order to eliminate d rho by rho in that expression, what I did was I tried to put something like dp by d rho as equal to the sound speed square, and I got all the relations coming. But does it have some implication? To be able to do that, let us do a simple experiment, or let us say a thought experiment. What is this thought experiment? Let us say I have a tank or a chamber, something like this. It is at ambient pressure, 1 atmosphere pressure. I am really not bothered about temperature at this point in time. Maybe I attach a convergent divergent nozzle to it. This is my throat, that means a constant area section. Let us draw it properly. Okay. Now what I do in this experiment which I am thinking of, maybe I collect all the air here, I put a pump here and I suck the air out of this particular nozzle. And what is the nozzle? I have this convergent divergent throat nozzle, and this particular contraption what I get, I attach it to the tank which is initially at atmospheric pressure. Here also the pressure is initially atmospheric, and then I start pumping out or start sucking the air out of this tank. Now what is going to happen? Let's plot, let's tell myself that the ambient pressure in the tank is initially 1 atmosphere, the pressure outside PE, or we say this is the tank which is the chamber, therefore I say PC is 1 atmosphere, let us say PE is also 1 atmosphere to begin with. When the pressure here and pressure here are same, obviously there is no mass flow rate. Therefore let us find out what happens if I attach a pump over here and start sucking out the air from this chamber. You know, this will tell us some clues on what really the sound speed, what havoc it plays, or what are the useful things we learn about sound speed. Let us do this experiment. Let us say I now plot the mass flow rate through the nozzle, that means the rate at which mass is getting sucked out, as a function of, let us say, the value of PE, that is the exit pressure to the chamber pressure. We told ourselves initially the pressure is 1, both are same, therefore the mass flow rate is 0, therefore the flow rate is 0. Then what I do, I start sucking out the air over here, I decrease the pressure over here. If I start decreasing, the mass flow rate will increase. That means as I increase the, or as I decrease the value of PE, PC being the same, the mass flow rate will increase. And therefore, do you think that as I keep on increasing, the flow rate should keep on increasing, or what should happen? Let's start thinking a little bit more. We tell, well, initially when the pressure outside is 1 atmosphere, pressure inside is 1 atmosphere, the velocity at the throat is equal to 0. Then I start sucking out. As I keep decreasing the pressure here, Vt will keep on increasing till it reaches a value Vt is equal to A. In other words, let us just plot till that time. I keep on decreasing the value of PE, that means I keep moving here, 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 till the time a stage has come at a given value of PE, let us call it a star, divided by PC, the value of velocity at the throat is equal to the sound speed A. Therefore, at that point in time, what is happening? Let us sketch out the nozzle in a bigger way. I left this gap for this purpose. I have the convergent, the throat, the divergent. Let us plot the value of the velocity at the throat, I call it as Vt. What has happened? Now for the same figure which I have drawn there, I have PE by PC as a function of Vt. What I find is initially it is 1, velocity is 0, the velocity keeps increasing till the time for a given value of PE star by PC, the value here is equal to the sound speed at the throat. What is the implication of this? Now what I find is the velocity at this particular point for this condition, when I have reduced the pressure to PE star, the velocity at the throat is equal to the sound speed. Now let us ask ourselves some foolish questions. We will ask ourselves this question: why is it the mass flow rate flows from this chamber to the outside? Because I suck something. When I suck something, what happens? I reduce the pressure here, and this information of a reduced pressure is transmitted through this over here, and that is why mass flows. That means I suck something, the information is reached there, and that is why something is flowing. Therefore, as I keep on decreasing the pressure, this tank senses that some information it reaches about this downstream pressure being lower, and therefore the mass flows. Now when the stage comes when the velocity at the throat is equal to Vt, and you know how does information travel? I talked to you, it travels at the speed of sound. Therefore any information here is traveling at the speed of sound, and this sound tells this chamber that I want something more. But if the gas is now flowing at a velocity Vt which is equal to the sound speed, and now sound speed is traveling, it cannot travel because it is the gas is flowing here, the information is flowing against it, it is at the same speed, and therefore no information can flow here, and therefore this becomes isolated. This chamber over here cannot get any information of the reduced pressure here when the sound speed is A, because information or disturbances travel at the speed of sound. Therefore, when Mach number is equal to 1 at the throat, what is going to happen? You know, I keep on decreasing, but the velocity here is the sound speed, and it effectively isolates, and therefore the tank is unable to know that a low pressure exists here, and therefore what is going to happen? The mass flow rate cannot increase any further, and the mass flow rate, it is not able to communicate at all, it is totally disconnected, and therefore I have something like this. In other words, for when the downstream pressure is such that I get the velocity at the throat to be the sound speed, thereafter the mass flow rate is a constant, and that means even though I am trying to pull, the information is not given to my tank, it supplies this, or rather I say that my throat is choked, and this is known as choked flow. I think this concept comes from the sound speed, and therefore we tell ourselves, well, when I have a convergent divergent nozzle at the throat, when I have the value of Mach number is equal to 1, it corresponds to a choke flow. In other words, any downstream disturbances cannot really affect my flow here. In other words, the concept of a throat and choke flow is central to the nozzle. I will continue with this in the next class. In the next class, what we do is we will find out the value of the density corresponding to the choke flow, pressure corresponding to the choke flow, and thereafter we will relate the area ratio of the nozzle, because we are still talking in terms of pressure, to the pressures, and talk in terms of flow separation and other problems with the nozzle in the next class. Well, thank you then. I think that is about it.